Over the lectures so far, we have talked about basic methods to process images. We talked about operations such as convolution, correlation, and then we talked about how we can use such operations to detect edges in images, corners in images, different kinds of corners, different methods to extract those corners, as well as how do you describe these corners in ways in which they could be used for further tasks. We also talked about how this process could be similar to how the human visual system also perceives the world around that we see around us. One of the aspects that we mentioned is if you have two different images and let's say you want to stitch an panorama consisting of these two images or more than two, we ideally detect interest points in both of these images, get descriptors of each of these points in both of these images, and then we match points across these images. How do you match is what we're going to get into next. So over the next few lectures, we'll talk about a few different methods to match key points between images. Not just key points between images, we will try to use these methods to do other kinds of tasks like finding different kinds of shapes in images, such as circles, lines, or whatever shape you like, as well as even more descriptors from what we've seen so far. Most of this week's lectures are based on the excellent lectures of Professor Yanis at the University of Rennes, Indria Rennes in France. If you recall, we gave this example earlier of two images taken of the same scene, perhaps from different viewpoints, perhaps at different parts of the day, or perhaps with just different illuminations or different camera parameters. And if you want to stitch a panorama of these two images, the standard process is to find key points and match them. So we know how to find key points in both these images individually. We also know how to describe each of those key points as a vector. We've seen SIFT, we've seen HOG, we've seen LBP, we've seen a few different methods to do this. The question that's left is, if you now have the key points and descriptors from two different images, how do you really match them and be able to align them? That's what we'll go into next. We'll start with a very simple method called dense registration through optical flow, a fairly old method which pertains to a setting where you have very small change between different images. So if you, again, taking the example of your cell phone, if you're going to gradually move your cell phone over a scene and then you want to stitch a panorama, the differences between successive images is going to be very little. So if you've tried this yourself, you will notice that in certain cases, if you move your hand very fast, you will get an error message to repeat and move your hand very slowly to get a panorama from the app on your cell phones. So in these kinds of cases, the displacement of the scene between successive images is very little. In these settings, you can use this kind of a method called dense registration through optical flow. Here is a visual example of a scene where a boat is going across water. You can see that the scene is more or less the same, but a few changes in the positions of the boats. Our goal here is for each location in the image, say a key point in the image, we want to find a displacement with respect to another reference image. Once you have a displacement, you can simply place one image on top of the other image and be able to align them. So this kind of a method of using dense registration is generally useful for small displacements such as stereopsis or optical flow. To understand how to do this, let's first take a one-dimensional case. Let's work out the math and then we'll go into a two-dimensional case. So let's consider a one-dimensional case. Let's consider a function f of x, which is given by this green curve. And let's consider this function g of x, which is simply a displaced version of the same f of x. Rather, mathematically speaking, I can say that g of x is f of x plus t. It's just a displaced version of f of x. And we also assume that t is small. We are only looking at small changes between successive images. We know by definition, by first principles definition of derivative, you can say that df by dx is given by f of x plus t minus f of x by t, limit t tending to 0, which would be the formal definition. But we know now that f of x plus t is g of x. So which means we can write df by dx to be g of x minus f of x by t. Where do we go from here? Now we define the error between these two signals in this particular case, because we're considering a one-dimensional equivalent right now, is going to be some weighted combination. Let's assume that this is very similar to the weighted autocorrelation that we talked about for the Harris corner detector. Just that in that case we talked about autocorrelation. Here we are looking at differences between two signals f and g. So you have f of x plus t and g of x. That's going to be the difference. And you do a weighted combination of these two to be able to find the actual displacement. So you have wx into f of x plus t minus gx square. Now this second term, this first term here, using a first order Taylor series expansion, can be written as f of x plus t transpose delta f of x. The remaining terms are the same across these two equations. The first term is simply expanded as a first order Taylor series expansion, and you get the right hand side of this equation. Where do we go from here? We know that the error is minimized when the gradient vanishes. So we take dou E by dou T, which we're just going to take a simple derivative of this right hand most term, which is going to be w of x, summation of x, w of x. That part stays the same as here. And the term that depends on t is this particular term. So if you take the gradient of that, you're going to have 2 into the entire term inside the brackets into the derivative of the term that's affected by t, which is delta of x. So you're going to have 2 delta of x into the entire term inside the brackets. We want to set this gradient to 0 and then solve for what we're looking for. So now, simply expanding this equation, you can simply take terms out on both sides and write this out as, we're just going to ignore the summation and the arguments just for simplicity of explaining this. If we ignore those, you'd have w into delta f transpose. These terms are branched here. Similarly, w into delta f into g minus f if you take it the other side. 2 doesn't matter here because they are anyway equating it to 0 and trying to solve for this. So now by doing this, you can solve for the delta f and be able to figure out the displacement between these two signals. What is the two-dimensional equivalent? It's exactly the same set of equations, just that instead of a 1D signal, you'll now have an image patch that's defined by a window W, and we then try to find what is the error between the patch shifted by T in reference image F and the patch at origin in shifted image G. So if you moved F by a certain T in the original image, do you get G is the question that we want to ask. We want to find that T that minimizes this change, because that would give you the displacement between F and G. Now by solving for this, you can get the value of T, find the displacement, and now be able to match or align these two images. A very simple solution. One of the problems of this approach is the same aperture problem that we dealt with when we moved from images to the Harris corner detector. Remember, the aperture problem simply means that you can only solve this problem for a very local neighborhood. Why so? Because the entire definition or the way we solved the problem assumed a local neighborhood. If you looked at the first order Taylor series expansion, that approximation holds only for a local neighborhood, which means this entire formulation holds only if the displacement is inside a very small neighborhood, and that's the reason why we said that this method works when there is only very small changes between successive images of the frame. So what do we do if there is more than a minute difference between these two images? For example, a few slides ago we saw those images of those mountain ranges. It didn't look like those two images were displaced by a very small amount. It looked like there was a significant rotation or a significant perspective difference in how those pictures were taken. How do you solve those kinds of problems? And for that, we'll move into what is known as wide baseline spatial matching. In wide baseline spatial matching, there's a difference from the dense registration. Just to repeat again, in dense registration, we started from a very local template matching process, and we found an efficient solution based on a Taylor approximation. Both of these make sense only when you have small displacements. But in wide baseline spatial matching, we're going to assume now that every part of one image may appear in any part of the second image. It's no more a small displacement. You could have a corner point that was lying in the top left of one image and the bottom right of the other image, and we still want to be able to match these points across these images. How do we go about this? The key intuition is going to be, we start by pairwise matching of local descriptors. So you have a bunch of key points in image 1 and a bunch of key points in image 2. For each of these key points, you have a descriptor. You now match those descriptors with the descriptors of all key points in the second image. Wherever you have the best match of descriptors, you're going to say that this point in image 1 is likely to match with this particular point, a certain point in image 2. And these points could be at completely different coordinate positions in the first image and the second image. So we start by pairwise matching of local descriptors with no other order imposed. And then we try to enforce some kind of geometric consistency according to a rigid motion model. So we know that in the real world, you can perhaps rotate an image, translate or move your camera or pan your camera. You can probably zoom in and zoom out. There are a few different transformations that's generally possible. All of them is what we mean as a rigid motion model or geometric consistency. So we're going to assume a particular model that could have taken place, and using these pairwise matching of local descriptors, we're going to try to solve what would be the parameters of the transformation between the two images. This is going to be the key idea, but we'll now talk about how do we actually go about doing this. So once again, in wide baseline spatial matching, you could have two images such as this, where a region in one image may appear anywhere in the other. There could be a zoom in, zoom out, it could be a different angle, or it could be translated by some bit. Any of those could happen when we try to do this kind of a matching. So as we already said, we first independently detect features in both these images. So each of them are different features that you see across these images. Then we try to do a pairwise descriptor matching for each detected feature. We can come up with a descriptor such as histogram of oriented gradients or local binary patterns or the variant of histogram of oriented gradients that SIFT uses, so on and so forth. You try to do a pairwise matching of the descriptors between the key points from these two images. Clearly, when there is a lot of change between two images, it's not necessary that every key point will match with some key point on the other. In this particular case, you can see that the car does not even exist in the second image. So any key points on the car would not have an equivalent match on the second image, which is perfectly fine with us. So only a subset of features that were detected in the first step would actually lead to matches in both cases. In both these cases, even in the first image, only a subset of features will match with the second image. Even among all the features detected in the second image, only a subset of features from the second image would match with features in the first image. How do you match? Once you get the descriptors in terms of vectors, you can simply take a Euclidean distance to match. You can use other kinds of distances too, but you can simply use the Euclidean distance between the descriptors of the features in both these images to be able to match. So once you get these tentative correspondences, we try to assume a certain geometric model. For example, we can say that we know that in our particular domain, only a translation is possible, or only a translation and rotation is possible because in my camera there is no zoom in or zoom out. It could happen, right? So if you knew what were the conditions under which a particular capture was taken, so you know what could be the transformation that could have taken place between the first image and the second image, or you assume a certain rigid transformation, and you find among those pairwise correspondences that we saw on the previous slide, which of them would hold true to this kind of a rigid transformation that I assumed. Okay. We'll come a bit later in this lecture as to how that rigid transformation is represented and how do we find out points that are inlier. We'll come back to this in a few slides from now. Okay. But this is the overall idea. So among all of those correspondences, you narrow down to a few which satisfy your hypothesis of what could have happened. And then once you get that subset of inlier correspondences, you can simply match and find the transformation and align one image on top of the other. So let's talk about this in more detail over the next few slides. So we first extract descriptors from the key points in each image. So for each detected feature, you could do something like construct a local histogram of gradiented orientations. You could do other kinds of things too. This is just an example. You find one or more dominant orientations corresponding to the peaks of the histogram. Remember, in SIFT, we talked about finding what is the orientation of each key points. That's what we're talking about here. At that point, you may want to resample the local patch at a given location, scale, or orientation based on what feature detector you used. You could have a scale for that particular key point. So you could have a location for that key point, you could have a scale, you could also have an orientation. So you could resample the local patch. When we say resample, if it's a rotated patch, you may want to resample it by doing some interpolation, so on and so forth, right? You resample the local patch and then you find a descriptor for each dominant orientation. That gives you your descriptors. Remember again, just like how we spoke for SIFT, you could take multiple descriptors for each key point if there are different orientations that are dominant. Okay, we talked about this earlier too. Okay, now at the end of that step, we have a bunch of descriptors in image 1, a bunch of descriptors in image 2. How do we go forward? For each descriptor in one image, we find its two nearest neighbors in the next image. Why two? It's just one method. You can also take other kinds of nearest neighbors if you like. In this method, we take two nearest neighbors and we then evaluate the ratio of the distance of the first to the distance of the second. So you have a distance between the descriptor in the first image to the first match in the second image, and the distance of the descriptor from the first image, the same descriptor, to the second closest match. If the ratio between the two is 1, which means both are good matches. If in one case the distance is very low, but in the second case the distance is very high, you perhaps now know which of them is significantly closer. You can threshold to find out which of them are strong matches. So whenever this ratio is small, you know that you found a very strong match because the second nearest distance is very far away. That's what this ratio would measure. So whenever you have a strong match, you're going to consider that a correspondence, and you then, after you do all these pairwise matchings, you have a list of correspondences between image 1 and image 2. What do we mean by correspondences? We are simply saying that descriptor D1 in image 1 corresponds to descriptor D10 in image 2. Something like that. You can just write out a table of correspondences between the descriptors of these two images. Okay, here is an illustration of the ratio test. So you can see here that for correct matches, you can see that the ratio of distances forms this kind of a distribution. It's much smaller, whereas for incorrect matches, the ratio keeps going up and further towards 1. Okay, in the incorrect matches, the ratio is going to be close to 1, which means the first match is as good as the second match. Then you're not very sure whether the match is strong enough. When the first match distance is much lesser than the second match's distance, you know that you're doing a good job. You can, as I said, also expand this to more nearest neighbors and expand the concept of ratio if you like to get a better idea of robustness of this match. Once you've identified these good matches, we move on and then try to estimate which of them are inliers with the rigid transformation that we assumed. Before we go there, let's first try to find out why is this a difficult process by itself. Okay, we've so far spoken about a few steps. Firstly, we have to choose key points or these kinds of correspondences which allow for a geometric transformation. Okay, that may not be trivial in several images. Fitting the model or the geometric transformation to the correspondences that we have found could be sensitive to outliers. It's possible just by chance that your correspondence could have been wrong, because in the new image maybe there was a newer artifact that came in which was not there in the first image, which ended up matching the key point in the first image. In that particular case, it could simply be an outlier match which could make fitting your geometric model a little harder. To find inliers to a transformation, you first of all need to find a transformation. So far, I kept telling you that you can assume a transformation, but assuming a transformation is not trivial. You need domain knowledge. You may perhaps need to do something more to be able to find out what should be the transformation in the first place before fitting these correspondences to the transformation. In certain cases, such as outliers, correspondences can also have a gross error. It's likely that in certain cases the correspondences can lead to mistakes. It's possible that HOG may not have been the right descriptor to get correspondences for certain features, so you could have errors in these kinds of cases. And inliers are often less than 50% of your total correspondences. Generally even lesser, but they're typically lesser than 50%. So which means the number of inliers that you're going to be left with at the end is very few that you actually can play with. So for the next part, to be able to understand how do you match these correspondences to the rigid transformation model, let's actually talk about what we mean by geometric transformations here, what do we mean by rigid transformations here, and then we'll come back and then try to align the correspondences to one particular transformation. Okay. Given two images I and I prime are equal at two data points x and x prime, we know that I of x is equal to I prime at x prime. This simply says that across these two images, you could map the point x to the point x prime in the second image. Or rather, you can write this as x prime is some transformation of x. We got the point x prime by perhaps rotating the first image, or by translating the first image, or by zooming into the first image. We're going to refer to all those kinds of transformations such as rotation, translation, scaling as a transformation matrix T. And what does T do? T is an operation that takes you from a vector in R square and gives you another vector in R square. Remember, any matrix can be looked at as a transformation in this perspective. So given a point, a coordinate location xy in image 1, the transformation matrix T takes you to another point x prime y prime in your second image. And this transformation is going to be a bijection, which means it's a one-to-one match between image 1 and image 2. Okay. Every point in image 1 matches to only one point in image 2, and every point in image 2 matches to only one point in image 1. It's going to be a bijection. Let's try to study what T looks like. T is a transformation. We said it's a matrix. So for a certain set of common transformations, T is fairly well defined, especially rigid body transformations. And this has been extensively studied, especially in the graphics based vision that we talked about in the first lecture. So we'll briefly talk about this now to understand how the matching is done. So suppose you have this green triangle in the first image and you translate this, rather you just move it slightly along the x-axis or y-axis or along the both these axes. It moves to a slightly different location in the second image. In this particular case, you would define the transformation to be given by a 3 cross 3 matrix, which is given as 1001, which is the top two cross 2 of this matrix. Then you have Tx, Ty, which corresponds to the translation along the x-axis and translation along the y-axis. If you work this out, and whenever you apply this transformation on x, y and 1 is simply used as a normalized coordinate to represent this transformation, we get an outcome which is x hat, y hat. Why so? Let's analyze this a bit carefully. It's simply a matrix vector transformation. If you simply did a matrix vector translation, you'll actually see that this is just another way of writing a system of equations. And the system of equations says x plus tx is equal to x prime. Similarly, you have y plus ty is equal to y prime. The third one doesn't matter. You're just going to have 1 is equal to 1. It doesn't matter. But this is exactly what we're looking for. This is just another way. This is just a system of equations. And we're simply writing the system of equations in terms of a matrix vector transformation, a matrix transformation on a vector to give you another vector. This is translation. Let's see one more. If you took rotation, this green triangle is now simply rotated. There's no translation. It's only rotated. You can see that 0, 0 is put here for the translation, which means there's zero translation, but there is rotation. And in this case, it's given by cos theta minus sin theta, cos theta in the upper 2 cross 2 of this 3 cross 3 matrix. I'll let you look at this more carefully. It's a simple expansion again. You would have x cos theta minus y sin theta is equal to x prime, and x sin theta plus y cos theta is equal to y prime. Okay. That simply represents the new coordinates based on your rotation angle theta. So you can see here that if you went back to the previous slide, in translation there are 2 degrees of freedom, tx and ty. In rotation, just 1 degree of freedom, which is given by the angle theta. Another transformation is called the similarity transformation, which has 4 degrees of freedom, which combines rotation, has 2 degrees of freedom due to translation, but you also have a scaling aspect here, which is given by r, which can change the size of the object in the second image. When we say size or scale, remember, it would correspond to zoom in or zoom out in terms of the camera parameters. So now you have r, theta, tx and ty, 4 degrees of freedom in this geometric transformation. Going forward, this is another example of a similarity transformation where you can see the zoom out in action, where the r has a non-zero value or a non-1 value to be able to show a similarity transformation where r is operational. Another transformation is known as the shear transformation. You can see here as to how the triangle gets transformed between the image 1 and image 2. This is known as shear, where you apply pressure on one of the sides of the triangle and extend it and keep the other sides perhaps constant. So this is given by changing just these quantities bx, by in your transformation, and the rest of them stay 1. So then it's called shear. You can write out the equations of shear as x plus bxy is equal to x hat, byx plus y is equal to y hat. This is simply a linear system of equation way of writing the transformation. Furthermore, a popular transformation known as the affine transformation is given by 6 degrees of freedom, where you can have values for any of those 6 spots in your transformation matrix that we spoke about. Okay. We're going to stick to these set of rigid body transformations at this time. There are certain transformations that also use these values at the bottom, which are going to projective transformations, perspective transformations. We are not going to get into it at this particular point in time. We're going to stick to affine transformations. So in all of these cases, as you can see, Using those tentative correspondences that we get between two images, we can find out which x prime matches to x and y in your image 1. So x prime y prime in image 2 could be matching with x y in image 1. So we already have a list of correspondences based on those matching of descriptors. Our job is to find out what are the parameters of this transformation T. That's what we want to look for. Clearly, this is about solving a linear system of equations. So we want to solve a linear system Ax is equal to b, where x and b are the coordinates of the known point correspondences from images I and I prime, and A contains our model parameters that we want to learn. Ideally speaking, if we had d degrees of freedom in a given transformation, you ideally need the ceiling of d by 2 correspondences. For example, for translation, 2 degrees of freedom, which means you need only one correspondence. If you have one point in one image and another point in the second image, you can find both tx and ty, because you would know how much you moved in x and how much you moved in y. So for given d degrees of freedom, you need about d by 2 ceiling as the number of correspondences from using your descriptors. Okay, now how do you solve for this, right? So we know now that, just to repeat what we've talked about so far, we found key points in each of the two images, we found descriptors, and then we matched the descriptors between these two images, and then based on the nearest neighbor approach, we pruned those descriptor matches to a few set of descriptor matches which are strong, and among those, we now want to find out which of them will suit my rigid body model that I'm going to assume for my transformation between the two images. So if I assume an affine transformation now, using those set of correspondences that I have, I ideally have to solve for these 6 values as my transformation. And once I have solved for these values, I know what was the transformation between these two images. So I can simply place one image on top of the other using the transformation again, and be able to blend them and create a panorama. So we are left with one task as to how do you actually estimate those parameters given those correspondences. Let's start with the most simplest approach that we all know, is if you have 2 points, fit a line. That's the simplest approach that we all know, the simplest model that we can imagine. Let's say that's the approach that we're going to use, but let's try to describe this further. So if you had a least squares approach to fitting correspondences, this is what you would have. If you have a bunch of correspondences here, this is clean data, not many outliers. The least squares fit would give you a fairly good equation for the line. Okay. We're just talking about the transformation in a slightly more abstract sense now, but we'll come back and make it clear as to how do you really estimate the parameters of the transformation. However, if there are outliers in your matches, then the least square fit fails and gives a very different answer compared to what should have been the right answer. So what do we do here? At this point comes to our rescue one of the most popular methods for matching features between images, which is known as RANSAC, or stands for Random Sample Consensus. A very simple iterative method, can be slightly computationally intensive, but works very, very well, has been used for many decades to be able to match correspondences between two images. For that matter, it can match correspondences not just between images, between any set of observations in data. So let's assume these are set of correspondences that we have. Okay. These are data with some outliers, and we ideally want to fit a line to this particular model. So we'll talk about fitting a line to data at this point. We'll then later come back to the analogy of taking this to fitting an affine transformation or any other rigid body transformation to a set of correspondences in images. So if you had such a set of data points and we want to fit a line to this particular set of data, what random sample consensus suggests to us is you take 2 points at random any 2 points. You can see 2 points that have been picked in red. Okay. We know how to fit a line for 2 points. So you fit a line for those 2 points. You take a neighborhood of that line on both sides and see how many points in that neighborhood are inlier points, or how many of them correspond to points that we are looking for. You can see here in green that there are about 6 points that are in the neighborhood of this line that was fit on these 2 points. Now you take another 2 points randomly. Once again, fit a line through those 2 points. Take a neighborhood and now count how many of your given data points lie inside this neighborhood. Now you can see that this is going to be a fair few. It's going to be about some 15 or 20, which is greater than the 6 that we got in the previous random pick that we had. What does this tell you? That this line may be a better fit than the previous line. So among all the lines that we've seen so far, we try to retain the line which has the highest number of inliers and throw away the previous lines that we came across. This is the line that we have now. You again repeat this process, pick another 2 points, pick a line, see how many are in the neighborhood of that line. Once again, you get a lesser number for such a line, and you keep repeating this process over and over again, but keep your best hypothesis saved with you. And you'll see that in this particular example, as you keep repeating this over and over again, this line that you have here, which goes through a set of random picks, is the best possible hypothesis, and that's the hypothesis that you're going to go with. That's the model that you're going to say that this set of outliers fits. Okay. So here are other examples of lines that you can draw, and in all of those cases, you know that the line that you had in the middle has the highest number of inliers in its neighborhood, and that's the one that you'll go with. Let's try to write out ransack more formally in terms of an algorithm. So given a set of tentative correspondences, okay, now we are looking at the correspondences that we started with. So you have a set of correspondences, which is your data. Let's look at n, which is the minimum number of samples to fit a model. Once again, remember, if you were trying to fit a model for rotation, it has 1 degree of freedom. So you at least need 1 set of correspondences to be able to solve the problem. Okay? That's what that 1 set of correspondences is what we are referring to as n here. And let's assume that in each of these cases, you're going to have a score Sx theta, which gives us the score of sample x given model parameters theta. Okay? Theta is just the model parameters that we are trying to learn. If it's rotation, you're going to have just 1 parameter theta. If it's translation, then theta would be tx, ty. If it's, this is for translation. If it's for affine, we already saw that you're going to have a11 all the way till a23, 6 such values. That's going to be affine, so on and so forth. Okay, those are your model parameters that you want to learn. So what ransack says is you start with the hypothesis, verify the hypothesis, and keep iterating and storing the best hypothesis so far. So you draw n samples from x at random. Let's call that set of n samples as h. You fit the model to h and compute the parameters. If your data are consistent with this hypothesis, most of your data are consistent with this hypothesis, you compute a score. If this score was better than the earlier score, you make the new hypothesis the best hypothesis, and you keep repeating this process. Let's talk about this in the context of matching features. So in this case, let's say you drew about say 2 different, or let's take an affine transformation which has 6 free parameters. So you need about 3 sets of correspondences to be able to get a good match between these two. So you draw 3 pairs of correspondences, the best correspondences that you have. You fit an affine transformation model, which means by fitting, you mean you can actually solve for a11 to a13 using a linear system of equations. Once you solve for using, when we say linear system of equations, using a least regression fit, you'll get a bunch of values a11 to a23. Now you try to see among all your correspondences, which of them would stay within an epsilon neighborhood of this particular transformation. Rather, you take all the points from image 1, which you were considering in your inlier, which you were considering in your tentative correspondences, apply this transformation, the transformation for which you now have A11 to A23 values. You would see where those points go to in the image 2. If for many of your correspondences, these matches lie within an epsilon neighborhood, you're going to consider that a good match, a good number of inliers, and the best hypothesis so far. And you just keep repeating this by randomly drawing 3 correspondences each time in case of an affine transformation. For a translation transformation, you just have one correspondence that you have to keep drawing to be able to fit these models. That's the main idea of RANSAC. Some limitations of RANSAC is when the inlier ratio, which means the number of inliers in data divided by the number of points in data, is unknown, then you could have problems in being able to fit. Also, when the inlier ratio is very small and the minimum number of samples to be drawn is large, let's assume that your definition of a model is such that you need to, let's say there are 12 free parameters, which means you need at least 6 correspondences that you need to draw to learn each model, and then you need to check for how many of them lie within a particular epsilon distance of the correspondences, so on and so forth. If your original inlier ratio itself was small in these images, then you could have a tough time. In this particular case, it will be equivalent to having about 10 power 6 iterations to ensure 1% probability of failure. Just to expand on this, I'm going to leave this for you to work this out by just giving a few hints, and you can work it out later. Remember that W is an inlier ratio, which means W power n is the probability that all n points that you picked are inliers. So you pick n points, that's the number of points that you have to pick to be able to solve for this model. And W power n is the probability that all n points are inliers, which means 1 minus W power n is going to be the probability that at least one of those points is an outlier. And when one of those points is an outlier, we're going to get a bad model which may not have too many correspondences in its neighborhood. If you run k different iterations, then the probability that the algorithm never selects a set of n points which are inliers, your probability is going to be 1 by 1 minus W power n power k. Okay, this should seem straightforward. Using these 3 terms, you should be able to work out why this would happen as an example here. Try working out by yourself. Here are a few visual illustrations of how well RANSAC works for different kinds of transformations. Here is an example of rotation. This is the original book rotated in a certain degree, and you can see that not a book, sorry, I think it's a foot box, and this is the foot box placed in a different place in the second image, and RANSAC finds fairly good transformations between these 2 settings. It also works well at estimating what is known as a transformation matrix or a fundamental matrix when you relate to 2 views of the same image. If you have 2 different views, remember this is how you would build a 3D model of a given scene. And if you wanted to build a 3D model of, say, the statue, you would ideally take multiple images by slowly moving around this particular 3D object, and you would get a 3D model. And in each of those cases, between every pair of images that you capture, you have to estimate this transformation matrix, which is also known as the fundamental matrix in this particular case. RANSAC is also used for what we started with in this lecture, which is to compute what is known as a homography, which is typically the term used for the transformation matrix in cases of image stitching. Right? We said that could be an affine transformation, translation, rotation, so on and so forth. That transformation matrix is typically called a homography when you do it in the context of image stitching. That concludes this first lecture on feature matching. We'll see a few other methods also as we go, but your readings for this lecture is going to be chapter 4.3 and chapter 6.1 of Seliski's book. As well as, if you're interested, the papers on the respective slides for more illustration, and the references are here.